We're going to introduce this new unit on gases by looking at a few things, mostly relating to the definition of gases and this concept of pressure. So if you look right here, this is a quick breakdown of the unit, and we'll mostly focus on this first bit, pressure. Before we move on, we've got to define what gases are. Gases, how do you define the term gas? This is a state of matter, right? So something that's a gas is something that is typically in the gaseous state at room temperature. So it's a state of matter, right? Gas is a form of matter where the particles are very spaced apart, and they are freely moving around without being held back. Whereas vapor, this is a term that's also included a lot in this conversation, and I just want to make sure the distinction is there. The two terms are not exactly the same thing. Vapor refers to the gaseous form of something that is normally a liquid or solid at room temperature. So again, the idea here is determining what something is normally at room temperature. If it's a gas, that means every single particle is in the gaseous state. But if it's a vapor at room temperature, we're talking about something that's mostly liquid, and then you can also see here in this little diagram that you have some vapor here, 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 and here. These vapor particles are particles that are in equilibrium with the liquid. So it's not like it's all of it is a gaseous state, right? It's only part of it is, and the large majority of it is probably in the liquid or solid state. Conversely, this gas, right, which is in orange here, these gas particles, these are all completely, again, freely flowing about. There's no actual solid or liquid state that's present. It's all gas at room temperature. And a quick comparison to other condensed states, solids, liquids, and gases. And again, their focus, of course, is on this guy. And the idea is that in one single state of matter, one single substance, you can have three different states of matter: the solids, the liquids, and the gases. And you can see that as temperature increases, right here in this first red line, as you go from left to right, it increases. And so what happens is that your states of matter will generally be the same, right? Or will also match, right? So your states of matter should make sense that gases are the result of increasing temperature. Which also kind of matches this next line, molecular motions, right? How quickly they're moving. So solids, again, these are moving very, very slightly. On the other end of the spectrum, gases are moving very quickly. They're not really represented right here in the static image, but you can imagine these bouncing around very quickly. And the last one right here, molecular interactions, is one we'll not really address at all. And actually, I'm going to kind of disregard it entirely for most of this unit. But basically, when they say molecular interactions, they mean molecular attractions. So how are they attracted to each other? As you can see here, right, the attractions that are present between all these little particles is pretty high, right? Because all of these are essentially locked into place. The attractions are so strong compared to the molecular motions, right? Compared to the movement. If you're on the right side, again, these particles are not attracted. There's no obvious attraction between any of these particles here. So you don't really expect there to be a whole bunch of conversation involving molecular interactions because the molecular motion, the movement of these particles is so great that they can't really be held back by those attractions. Let's define pressure. Pressure is probably something you are familiar with. So we're going to define it quickly just using a formula. After this line here says, the definition of pressure is the applied force per unit area. So first of all, to represent that, we're going to use the symbol P, capital P representing pressure, is equal to the force that's applied over a area. Now, area, of course, is a two-dimensional space unit of some kind of area. It doesn't really matter in this case. We're just getting an idea. So force per area. So when you think about this, right, let's say when we have a conversation about, say, for example, a sharp knife versus a dull knife, right? So let's say we have a sharp knife. If you're looking down the edge, right, this right here is the point at which it makes contact with, like, say, for example, a slice of bread. So when you try to cut the slice of bread, right, you have a very, very fine point. That means whatever force you apply as a very small area, right, there's not a lot of surface area that makes contact with the bread. So that means you can apply a decent amount of pressure even though you're not pushing very hard, because that very, very small amount of force, whatever it might be, is actually spread out over a very even smaller amount of area. But if you have a dull knife, right, so a dull knife pushing up against, again, a slice of bread, that would actually end up not really cutting very well because you have such a big surface area here. So that denominator is larger, so the pressure that you apply to it is going to end up being small. Even if you put the same amount of force on the sharp knife as you did the dull knife, right? So as you push down the same amount of force on both of these because the surface area makes such a big difference. But of course, knives are great and all, but how exactly does that relate to gas particles and their behaviors? Well, if you look in this diagram here on the right side, this is kind of, again, a little particle diagram of how gas particles are behaving. And you see that these gas particles are moving about And it's showing the path of a lot of these as they sort of bounce around and hit this and hit that. Some of these are longer than others. Some of these are shorter than others. So we need to kind of sort of define how exactly this gas pressure is defined. So what exactly is the force when we talk about gases? And this is an important distinction you need to understand. The gases, right, the particles there, are the force is actually the force that comes from the actual impact. So when these particles hit the walls, right, when it smacks into the walls and it moves around to another place, that force of impact is what they mean by force, right? So actually hitting the particles. Whereas the area refers to the overall surface area that the container holds. So the internal surface area, all this space here, everything that is outlined, all that's your surface area. As you can imagine, right, you can figure that out fairly easily with these flat surfaces, what the surface area is, and that is your area. So the force of the particles hitting the walls divided by the overall surface area of the container. That's how you define pressure when it comes to gas particles. Let's go and keep that idea in mind because we refer to this concept quite a bit throughout this unit. So remember that when we talk about pressure, right, it's always defined by how the particles hit, how hard the particles hit over a certain area. So as you can imagine, right, if let's say we have in this force per area little formula here, what if I have particles that hit really hard compared to these particles in this, right? If they hit really hard, that means they have a higher pressure because the surface area stays the same and the force goes up. On the other hand, what if I took this and put it into a much larger container? I'm going to have the same number of particles in there. I think there's about 15 of them there. And these particles, again, are spread out in this larger area. Well, again, the force at which they hit the walls is the same, but the denominator, the area that is contained in all the surface area of the inside of our container, all that increases, so the pressure decreases. We're going to do a lot of comparisons here, talking about the pressure and whether or not it increases or decreases. So it's important to keep this concept in mind of the particles hitting the walls. Finally, how do gases move? Now, how do gases move from one place to another? This is going to be a little bit difficult to understand at first, but I think you get the hang of it with some practice. Effectively, the language that you would use here is that gases move from areas of high pressure to low pressure. Right now, that seems pretty okay to understand, but how exactly do you have higher pressure or how do you have lower pressure? How do we sort of quantify that? That's what we're going to get into a lot here. Let's start with atmospheric pressure. This is a concept that you'll want to have down. This concept is related to the pressure that comes from our atmosphere, right? Because our atmosphere is made of a lot of little gas particles. Those gas particles extend all the way from the surface of the Earth all the way up to the outer edges of our atmosphere. So all of that together, collectively being pulled down by gravity, generates a certain amount of pressure. All those particles that are smacking into each other and then furthermore smacking into the Earth, that again is what we use to quantify atmospheric pressure. So if you can imagine, right down here, you imagine 10 by 10 meter or 10 meter by 10 meter square of Earth, right, and then extend that column all the way up to the outer edge of space, or the outer edge of the Earth anyway, the Earth's atmosphere. All of that air pushing down is going to generate a certain amount of pressure. So all the particles that are up here, right, they kind of smack into each other, which then smack into these particles here, which bump into these down here. And all these particles that run into each other, when they run into each other, again, they generate a force. And so eventually it all can be quantified as it pushes down on that 10 by 10 meter square, or 10 by 10 square meter of Earth. Now, of course, this is at sea level, so I'm going to make sure to think about this sort of at the beach or at some very, very flat surface close to the ocean. And then that is defined by 1 atmosphere. That kind of makes sense. Right? This is a standard pressure measurement, 1 atmosphere, because that's how much 1 atmosphere weighs. Effectively, how much pressure that 1 atmosphere will push down on the surface. How do we then measure that? Well, how we do that is by using something called a barometer, B-A-R-O, barometer. This barometer is useful for measuring open pressure, meaning a general area of air or whatever room you're in or whatever environment you're in. We're not always going to be at sea level, so we can't always just use 1 atmosphere for everything. So a couple of things you need to know. One, this is going to be a mercury barometer. Mercury, because mercury is used in this. Yes, that very poisonous liquid mercury. This sort of apparatus here is how they do so. So you kind of have to get used to a couple of things. First of all, this is like a little glass dish, like a pretty big glass dish. And then this right here is basically an inverted tube. So if you can imagine a long, skinny test tube, this long, skinny test tube is kind of, like, you can't really see it in this, but maybe cuts off about here or so. And then like mercury can kind of go in or mercury can go out as necessary. And so what happens here is that the pressure of this atmosphere, or so atmospheric pressure, can push down on this liquid. And what happens then, as a result, is that the mercury goes in up to its very specific height. Please do note that there's a vacuum in this as well. We'll kind of get into what that means in a little bit. But this glass tube right here has a vacuum up here, and then this atmospheric pressure can push up. And then what it turns out to be is that this height, right, from the surface of this liquid, the surface of the mercury that's in here, that ends up being a distance from the top of the mercury in here, a distance of 760 millimeters. 760 millimeters, that's about 29 inches. That's a little bit, it's about maybe 3/4 of a yard or so. That's a pretty significant height there. So that's a lot of mercury. And we'll talk a little bit more about why they chose that. But again, this is assuming that we're at the atmospheric pressure. We're assuming we're at sea level here. So if you brought the barometer up to Nashville, which Nashville is very much not at sea level, it's significantly higher, would the column of mercury be higher, lower, or unchanged versus at sea level? So would this level right here, would you expect that level to be higher, lower, or the same if you took it from sea level up to Nashville? So I want you to think about that, and we'll talk about the response when we come back. Some other equivalent units of pressure. So you have 760 torr, T-O-R-R. That name comes from the individual, I think his name is Evangelista Torricelli, who again defined a certain value of pressure, and it turns out it's the same as the 760 millimeters of mercury, 760 mmHg. Millimeters of mercury, which represents that mmHg there. So 760 millimeters of mercury, 760 torr. As you can tell, they're the same thing. Also equivalent is that 1 atmosphere that we addressed earlier. So that 1 atmosphere of pressure is also the same as 760 torr, 760 millimeters of mercury, as is 101.3 kilopascals, represented by kPa. K, of course, meaning kilo, and then PA referring to the unit Pascal. Now, a quick comment here. This actually, the PA, Pascal, is actually the SI unit for pressure, meaning it's the one that the scientists, again, generally assume to be the most basic form. But more often than not, we'll end up using any version of this, or this millimeters of mercury, those units more frequently than kPa. But also just note that PA, at 1 Pascal, is just a very small amount, so usually represented in kilopascals. Let's go and take a look at this. I'm giving you a couple of pressure measurements, and I'm asking you to convert between them. So as you can tell by the previous slide there, you have a couple of equivalent quantities. That means you can kind of set up some conversion bridges and conversion factors. So I'll do the first one with you here. It says to report the following pressures in atmospheres, torrs, or millimeters of mercury and kPa as necessary. So let's do the first one together. That's going to be 200 point kPa. I'm trying to relate, let's say, kPa to atmospheres first. So let's do atmospheres and kPa. And that's going to be 101.3 kPa for every 1 atmosphere. All right. How do you know that? Well, again, on the previous slide there, it shows you that those equivalent measurements are also therefore used as conversion factors. And so you can set it up like this, and you should be getting 1.97 atmospheres. Quick note, kind of scooching back up here, all these measurements, 761, 101.3, 760 up there, those are all actually going to be considered infinite significant figures as they are constants. Right? They're defining a specific quantity, so they're not going to have any guessed or estimated values there. A couple of the thoughts on pressure. First of all, the term vacuum. This is a strange one to sort of encounter. Just note that this is not really talking about like vacuum, the vacuum cleaner, which most of you probably initially associate with this. A vacuum is just a space that is completely devoid of matter. So I kind of want to focus on this area of that mercury barometer that we pulled from a previous slide. That mercury barometer, again, it says that there's a vacuum in here, meaning that if you were to look really, really closely, right, again, whenever you expect there to be empty space, you might expect there to be some gas in there. Well, it turns out the way that this is done is that there actually is no gas in there at all. There's nothing in there at all. So literally, there's no air particles in here, right? So if there's no air particles, that means that's called a vacuum. There's absolutely no space in there. And then the other part of this is that how this works with your atmospheric pressure. Right? How exactly does this do this? Well, again, we talked about this earlier, right? How exactly do things move, or how can we kind of make gases move, or how do we address that? Well, again, it's moving from higher pressure to lower pressure. And so since this, again, has mercury in here, or had a mercury in here, this atmospheric pressure is going to push down on this. But there's nothing else pushing down on here, right? There's no other force of air pushing down on this. So really, it's atmospheric pressure is pushing up against this empty space in there. Yeah, it's a little strange, but just recognize that vacuums, when we talk about that, that means there's 0 particles in there. So if that means there's 0 particles, what's the pressure have to be? That's going to end up also being 0. You might have a surface area on the inside, sure, right? But what force is there? What particles are pushing against the surface? And that's none. That's 0. That's why the pressure in here is considered to have 0 millimeters of mercury or 0 atmospheres or whatever else that you want to use for measuring pressures. Another term you might hear a bunch is the term negative pressure. Negative pressure, first of all, isn't really a thing, right? Negative pressure, for example, is kind of looking at the second bullet point. It doesn't really exist. For example, is it possible to have negative 200 millimeters of mercury? Now, that might not make a whole lot of sense yet, but no, it's not really possible to have a negative pressure because that assumes that somewhere in this force per surface area formula that you have a negative force. Can you apply a negative force? Can you push something? Or area, can you have a negative surface area? I don't think so either. So this is not really a thing. Negative pressure is not a thing. Really what they're saying is that there is some kind of a difference in an environment compared to some sort of pressure inside something. So, there's some kind of situation where there's a difference in pressure inside versus outside. So that's what negative pressure means. So you might hear that from time to time, and maybe not in this class necessarily, but out there. Just know that that's not really a thing. It's about the difference. It's the fact that there's some pressure in two different sides, just that one's a lot less than the other. And the last point on here is asking you, how does a vacuum cleaner pick up dirt? So then I kind of mentioned the vacuum cleaner again. How exactly does a vacuum cleaner pick up dirt? Right? You run the thing, run over some surface, and all of a sudden it disappears, gets sucked in somehow. Let's kind of think about that. Sort of address how exactly that works. How do you measure non-atmospheric pressures? Right, so of course there's some situations where we're not going to have open air that we have to get the pressure of. That's going to be something that requires, a new device called a manometer. So a manometer, we'll talk about how it works on the next slide. But really, again, this is making sure that we can get pressures that are not from from the atmosphere. It's all contained inside of a vessel. So sliding on here for a quick second, you see this right here. Again, we're assuming that this is a gas that's inside of some kind of container where we maybe did some reactions or we put some gas in there. Right? That's not exposed to air. Right? This is not, again, just atmospheric pressure in here. So that's why we use this manometer. Going back up real quick also, the similar principle in terms of measuring pressures is exactly how they measure blood pressure on your arms. There's cuffs that go around your arm, and this is a sphygmomanometer, just a little side trivia there. But again, it's a manometer of some kind. All right, the sphygmo, I'm not really sure what that prefix means. Just know that has something to do with measuring pressure, and they do so by using some form of what's going on here. So let's go and break this down. Let's look at the left one. The left diagram here, if you notice, you have this chamber that has some gas in it, right? And also you have connecting through this tube right here. This section right here is mercury. Now, normally this mercury would be sort of in between, right? It'd be kind of resting in the middle. But because we put some pressure in here, we added some gas in here, it's going to be moved around just a little bit. So one thing I want to point out is that you're going to find that this right here is going to be compared to atmospheric pressure. So this gas in here are effectively comparing atmospheric pressure. And so this mercury that's in here can be pushed around a little bit. And so it's kind of like a little mini kind of comparison. So if you see that this side right here is higher up than this side, that means that atmospheric pressure pushing down compared to the gas pressure pushing here, atmospheric pressure is higher than the internal pressure there. Therefore, this pressure right here pushes the mercury down, and this side goes up as a result. So that means, again, if I wanted to figure out how much pressure is in here, what I'm going to do is I'm going to notice that the pressure of the gas is equal to atmospheric pressure minus this height between the top of the mercury and the bottom of the mercury within this tube. All right. Over here, though, on this side, right, you still have another gas chamber. This chamber right here is connected through this, or at least has a little column of mercury. And you still have it exposed to atmospheric pressure, which can push down. And that pressure that pushes down, in this case, ends up being less than the pressure that's inside this container, right? So whatever force is pushing on here compared to the forces being pushed there, the pressure that's being applied there. And so you notice that the pressure is greater inside this chamber than atmospheric pressure. So to figure that out, we take atmospheric pressure, we add the height of this column of mercury right here to get the pressure of the gas that's inside there. So you're going to have to first look at the difference in pressures, look at the heights of the mercury, and then either add or subtract it depending on the problem. This also gives you a couple of visuals. So on the right side here, this is the open-end manometer. This is what we just talked about. On the other side, though, we have the closed-end manometer. So the closed-end manometer effectively is functioning almost similarly, except this time you're not actually using a actual atmospheric pressure to compare. Notice that you have the end here is closed off, right? It's closed. So that means we don't exactly have a manometer that's using atmospheric pressure like we see here, right? Where we have atmospheric pressure pushing down, atmospheric pressure pushing down. And instead of have a vacuum where the pressure is about zero, we effectively treat it as zero. And so how this works then is that, if you have 0 atmospheres in here, right, whatever's pushing here, there's not really anything pushing against each other. But the second you put something with pressure in it, right, so let's say we have a container that has 1 atmosphere of gas in here, that gas is going to push down on this mercury on this side. But this side, again, there's nothing pushing down on this, right? There's nothing sort of counteracting that, trying to push against it. So because of that, you end up having this distance, this height right here, right? That's still some distance h. But again, in this case, right, the pressure of the gas that's in there, right, that's going to be equal to 0, right, whatever it is, there's no pressure against this, plus this height. So basically the pressure of the gas is the pressure of the height. So whatever height that's here, let's say it's like 25 millimeters of mercury, like 25 millimeters of distance between the top and the bottom here. That means you have 25 millimeters of mercury of pressure inside of this. Now, again, that's actually not accurate. This should be more like 760 millimeters since we are assuming that it's 1 atmosphere. But let's say again that this height right here is actually 760 millimeters from here to here. That means we have a pressure of 760 millimeters millimeters of mercury inside of this gas chamber, which is again equivalent to 1 atmosphere. Go and take a look at this one example problem. You'll see the answer at the bottom left to kind of double check your work, and that'll do it.